In this presentation, I will go over what wavelets are and how they are structured on the wavelet transform. I will explain the benefits of using wavelet transform compared with other signal processing techniques. Thanks to our class, we've learned that Fourier transform is a useful tool for converting time domain signals into frequency domain signals. However, when we want to know about time, Fourier transform is not very useful because the signal frequency components are constant over time. This means that if you have three different music tones, do, re, and mi, the frequency domain will always display the same three peaks, no matter what order you play them. This limitation makes it hard to analyze non-stationary signals, or in other words, signals where the frequency and time characteristics change. To address this, we need a method that can provide both time and frequency resolution, a way to observe how the frequency content of a signal evolves over time. The short-time Fourier transform, also known as STFT, tries to solve this by dividing the signal into small overlapping segments and applying the Fourier transform to each segment. While this provides some time-localized frequency information, it is constrained by the size of the window. In other words, a large window offers better frequency resolution but poor time resolution, and a small window does the opposite. This fixed resolution trade-off limits its utility in the real world. So, how can we know both frequency and time information of a non-stationary signal? I introduce to you wavelet transform. Unlike the Fourier transform, which uses sinusoids as its basis functions, the wavelet transform employs wavelets. Before I explain what wavelets are, let's understand why we need oscillation to analyze the frequency of signals. When we use the Fourier transform, we break a signal into a sum of sine and cosine waves. These sine and cosine waves act as the building blocks for representing the signal in the frequency domain. It's like looking at the signal through trigonometric glasses to view everything as a combination of sines and cosines. However, the sine wave comes with a problem. It's infinite and periodic, so it doesn't give any sense of time. But what if we change it a little bit? We need up and down oscillations because this is the foundation of frequency representation. But is there a way to restrain it in time? The unique thing about a wavelet is that it is short-lived wave-like oscillation, which is localized in time. But what exactly is a wavelet? Mathematically speaking, a wavelet is not just one function. It's a bunch of functions which satisfy certain requirements. The first requirement is that it should have a zero mean. So, as you may know, this means that if you take the integral or area under the curve where the function exceeds zero with a plus sign, and areas of the curve where it dips below zero with a minus sign, and add them together, you should get zero. If we look at the sign down below, we can notice that a sine function passes this condition because the average value is zero. But a sinusoidal wave breaks the second requirement on a wavelet, which is having finite energy. If you are lost by the term finite energy, this condition says that if you square the function and compute the area under the curve everywhere, from minus infinity to plus infinity, it should be a finite number. And this is exactly what makes the function localized in time. If we square a sin wave and compute the area under the curve, the wave is infinite. Know that we know these two requirements? Let me show you the different types of wavelets used for signal processing. Some of the most common wavelets include the Haar wavelet, which is ideal for piecewise constant data like images. The WT wavelets are a family of wavelets with varying levels of smoothness and compact support, making them versatile for tasks like denoising and compression. There is a silly one called the Mexican hat wavelet that is used for detecting peaks and ridges in signals and images, and there are many more. Now that we have our little wave, what do we do with it? Well, let's clarify that the mathematical representation of the wavelet is phi of t, also denoted as the mother function. I'll explain why it's called mother function in a second, but first let's clarify that we have two parameters we can change in wavelet transform. The key difference of wavelet transform is that instead of having one-dimensional function, we would now represent it as a two-dimensional surface, where one axis represents frequency, just like in the case of Fourier, and the other axis represents time. Our output value in our wavelet function is a contribution of frequency f at time t. But how do we do it? Well, this time, we're going change t and f, meaning change frequency and time. When we change these two parameters, we essentially modify our initial wavelet function, which I earlier called the mother wavelet, to obtain new, slightly modified versions of the mother wavelet called daughter wavelets. By changing the time parameter, we translate or move the mother wavelet along the time axis back and forth. And by changing the frequency, allows us to shrink or stretch the mother wavelet along the time axis. If you stretch the wavelet by a factor of 2, its frequency will become 2 times smaller, because the number of cycles per second is now twice as small. And likewise, shrinking the wavelet increases its frequency. Combining these two modifications of the mother wavelet, let's define the scaled and translated wavelet as this. Then the value of our wavelet transform at a particular scale, A and time B, would be equal to the contribution of that scaled and translated wavelet to our signal. But what do I mean by the contribution? Well, you can think of this contribution as the goodness of fit, a measure how well our modified wavelet matches the signal around that time point. This means that the wavelet transform measures how closely a wavelet, a scaled and shifted version of the mother wavelet, resembles or aligns with the signal at a particular time and scale. Another way to think of this is if the wavelet's oscillations and shape closely resemble the signal's features like peaks, valleys, or patterns around time B, the contribution will be large. If the wavelet doesn't match the signal well at that time and scale, the contribution will be small or near zero. In mathematical terms, this goodness of fit is calculated as the integral, or summation in discrete cases, of the product of the signal and the wavelet. When the product is large, it means the wavelet and signal are in sync, indicating that the wavelet captures a significant feature of the signal at that specific scale and time. In summary, we've explored how the wavelet transform overcomes the limitations of the Fourier transform by providing both time and frequency information for analyzing non-stationary signals. Unlike the infinite and periodic sine waves used in Fourier analysis, wavelets are short-lived oscillations localized in time, making them ideal for capturing how a signal's frequency content evolves. By scaling and shifting the mother wavelet, we create a set of daughter wavelets that help us measure how well the wavelet aligns with the signal at specific times and frequencies. This capability to adapt and localize in both time and frequency makes the wavelet transform a powerful tool for analyzing complex signals in various applications. Thank you for watching this video.